Howdy, my name is Kevin Zhang from Texas A&M, and my mentors are Amber Black, Cheryl Hawk, Kayla Molnar, and Lindsay O'Brien of Los Alamos National Laboratory. I will be discussing two projects, the first being a welding and joining database, and the second being the weldability of 17.7 pH stainless steel. My goal for the database was to revamp the current homepage with one that was built from the ground up, specialized for the welding and joining team. The focus is to add functionality necessary to bridge the homepage with data. However, robustness and room to update the page down the road were other important considerations. The database is accessed across all sorts of devices, so maintaining the same proportions and clarity across all browsers and resolutions was a priority. The webpage is written in HTML, CSS, and JavaScript, with jQuery and Slick being popular JavaScript modules used to build the image carousel. The webpage has 3 tabs, but they are all consolidated into a single HTML file which provides instantaneous load times. The other interactive elements include a flowchart map that interfaces with the database file tree and search boxes with suggested entries and blank input failsafes. Attention was given to many small details with the webpage. A database prioritizes ease of use above all else, but that doesn't mean graphic design elements were overlooked. An example can be seen with the 2 buttons. Simply changing the cursor and adding a hover effect provides the bottom button with much better input feedback. The details extend into the code, where comments and IDs aim to future-proof readability. To create a sleek look familiar with the rest of Los Alamos' resources, the brand guide was applied to the webpage's elements. The color palette, font family, and icons were all referenced in the code. The final step was to upload the completed webpage onto Granta.mi, the program hosting the database. ANSYS documentation provided examples of the commands necessary for the code to call out, along with how a file should be organized in order to be identified by Granta.mi. Still, the process did not go as smoothly as intended. Changes had to be made to both the webpage code and the database settings for the two to interface correctly. After troubleshooting all the inconsistencies, the homepage is working as expected. The green box in the diagram shows where the webpage is positioned within Granta.mi. Unfortunately, as a remote student without access, I cannot demonstrate the webpage working within the Granta.mi environment, but I can show off the otherwise identical webpage in its own browser. This is a look at the welding and joining team database homepage. To start, we have an About section that just tells a little bit about what the team does. Following that is the image carousel. Each of these categories, when pressed, will apply a predetermined filter on a search bar. Following that is the search boxes. Each of these will allow for more refined searches. Here's a demonstration of the failsafe for the empty inputs. Our next tab is the map. Pressing any of these buttons will open up a file tree that is typically on the left if this was in a Granta.mi environment. Finally, this is the Help tab. We have contact information for each of the team members, along with tutorials. To demonstrate the proportional changes for different monitors, I will zoom out of the page. You can see at each zoom level, the website does its best to maintain the proportions. That way, people with larger monitors will still have the same experience. Moving on to the second project, my goal was to explore viable methods of welding and treating 17.7 pH stainless steel to see what combination produced the best results. The 17.7 in the name refers to the chromium and nickel percent composition, and the pH refers to precipitation hardening. Criteria for success included 90% strength retention of the base stainless steel and qualitatively ensuring distortion was minimal. Empirical data was collected for 3 different weld processes and 3 different treatments to be compared. The three welding processes analyzed were electron beam welding, gas tungsten arc welding with filler material, and gas tungsten arc welding without filler material. Electron beam welding works by accelerating a very narrow beam of electrons into a workpiece within a vacuum chamber. EBW is a machine-operated process and has high equipment costs. On the other hand, gas tungsten arc welding uses an electrode with a shielding gas and optional consumable filler metal. GTAW is done handheld and requires great precision. EBW leaves behind a deep and narrow weld bead, whereas GTAW leaves a shallow and wide bead. The post-weld treatments analyzed were the as-welded condition, welded and aged condition, and welded, annealed, and aged condition. The steps for each treatment can be seen in the graph. Because we are dealing with a precipitation hardening stainless steel, it is expected for heat treatments to make a considerable difference in the strength. This is a look at the experimental setup. We have 4 pieces of 17.7 pH stainless steel. The first will not be welded to act as a constant, while the other 3 will be welded in a straight line using the electron beam, autogenous gas arc tungsten, and homogeneous gas arc tungsten welding processes. Following that, each piece will be cut into thirds to undergo the 3 different heat treatments. Finally, each sample will have its micro-hardness measured on a cross-sectional grid. There are many factors that cause distortion, and analysis will be done mostly qualitatively. Distortion occurs when the metal expands and contracts, producing internal stress. Therefore, welding a smaller area and using less heat are the important advantages for electron beam welding. As mentioned earlier, EBW welds a narrow area and is machine operated, meaning travel speed is drastically faster than GTAW and the material will only be passed over once. All these parameters culminate in EBW having lower heat input and therefore lower distortion. During the experiment, only hardness data was collected for the sample cross sections, but it has been shown that yield strength and tensile strength have linear relationships with hardness. Using relevant figures for stainless steel, the 90% strengths were calculated for the base material and compared to the minimum strengths for each sample, as shown in the color table. The only sample to pass the criteria was electron beam welding with the annealed and aged treatment. However, the whole story cannot be told without also analyzing heat maps. These are a few of the heat maps generated from the hardness data. The base metal, as expected, has a strong uniform hardness throughout. When we weld without any heat treatments, the weld bead left behind is visibly weaker than the parent metal, as indicated by the strong red center. The aging treatment does not affect the bead, but hardens the surrounding area, shown by the adjacent blue tiles. It is only after annealing and aging that the sample develops a strong and uniform cross-section. This is to be expected, as the annealing process is when precipitation hardening occurs, along with changes in the microstructure. The GTAW heat maps are not shown, but they had similar results with EBW. The differences were in a shallower, wider weld bead, along with a rougher, more discrepant color gradient. To summarize, electron beam welding with the annealing and aging heat treatments produced the best strength. It should be clarified that the heat treatment played a much bigger role than the weld process used. This was to be expected for a semi-austenite precipitation hardening stainless steel. It can be inferred from the nature of electron beam welding that it will produce less distortion than gas tungsten arc welding due to the lower heat input and narrow weld beads mentioned earlier. Still, gas tungsten arc welding has its place as a more traditional and accessible method of welding with passable results when put through the proper annealing and aging processes. I would like to express my appreciation for this opportunity to collaborate with Los Alamos under A&M's OREU program. This is my first experience with formal research, and I am grateful to have been able to learn more about the field of material science with guidance from an excellent group of mentors. Thank you.